This podcast is brought to you by LMU Munich.
Okay, so thank you very much to Oliver and Dennis for organising this. Maybe I'll start off by explaining why this is just a very strange picture, and it's going to appear on every slide because that's the way this beamer theme works. So I have this beamer theme that needs a picture, and what I usually do before a talk is I Google a couple of keywords and find an appropriate picture. And I Googled gravity and inertia, and this came up. And this turns out to be an Xbox game in which you can turn on and off the gravitational field. And it's called Inertia. So if you think it's ugly and horrible, which it is, it's just because it amuses me. All right, so what am I going to do today? Perhaps I should say this isn't exactly a paper. This is kind of, I've done a lot of work that's effectively work on theories that split up gravity and inertia or recombine them. And so this is a kind of, I'm going to try and bring some of the ideas in that work together. And in particular, I'm going to try and bring it together in a way that really highlights the features of general relativity that makes its reduction of gravity to inertia particularly compelling. So I'll look at Newtonian gravitation with and without a gravitational split. That is, geometrized Newtonian gravitation as well as standard Newtonian gravitation. And then I'll introduce what at first sight looks like a way to perform the same kind of trick in general relativity. So there's this theory called Teleparallel gravity. And it claims that what it does to GR in an entirely empirically equivalent context is it splits up the connection into a gravitational and inertial part. And I think it fails, and I think it fails for interesting reasons, and I think it fails for reasons that teach us something about how hard it is in the GR context, in a context that's empirically equivalent to GR, to perform this split. And as I say, this sort of isn't sort of a cohesive paper of mine. So one thing, because I kind of want to draw everything together, I'm going to kind of finish by kind of putting in a plug for the paper that Jim Weatherall, John Manchak gave on Monday, which talks about possibilities for conventionalism in the GR context. I think that's kind of relevant here, so I'll say a little bit about it. So let's just let's take a kind of first shot at how you might think a table of possibilities of theories work. So you've got three kinds of things you might try and do with gravity and inertia. You might try and have a theory that has no split. So I'm going to interpret GR as a theory like that, contra these kinds of frame-dependent subtleties that Oliver and Dennis were talking about at the beginning. Or you might try and make a split in a principles kind of way. So you might try and come up with a theory with some equations, some field equations, that told you how to split up gravity and inertia. Or you might try and make an arbitrary split. You might just want to assert that, forget about whether you have nice equations, you can kind of carve your inertial field up into a gravitational and inertial part. And you can do this either in a Newtonian context or in a GR context. What I mean by context in this context is just you're looking for a theory that's at least locally empirically equivalent, locally in a fairly broad sense of local, to Newtonian mechanics or general relativity. Empirical equivalence is a little bit tricky in these contexts because GR has topologically non-trivial solutions, and once you have topologically non-trivial solutions, you end up with a theory that's very sensitive to reformulation because, say you reformulate in terms of a tetrad field, you might prima facie rule out some topologies. But I'm going to brush all that under the table, and I'm going to be thinking about sort of empirically equivalent pairings, and empirically equivalent pairings that you can prove are empirically equivalent because there's some principled relationship between them and the original theory. So in the Newtonian context, we have geometrized Newtonian gravitation or Newton-Cartan theory, same thing, just two names for the same thing, and that's the no-split theory, and then we have standard Newtonian gravitation that splits up gravity and inertia, and then perhaps we have conventionalist theories that enact an arbitrary split. And at first glance, at least, and it's this right-hand column that I'm going to question, in the GR context, you have general relativity that has no split, you have teleparallel gravity, and perhaps other theories. I'm certainly not going to deny that there may be many ways to skin a cat, although I'm going to put some restrictions on it, that would introduce a principled split, so some empirically equivalent theory with a properly developed set of equations that introduce a principled split. And then you might have some equivalent of conventionalism. So you might have some kind of arbitrary way to carve up GR into a gravitational and inertial part. And I think what's sort of interesting is that while as you were facing, the left-hand column is going to kind of end unscathed. Newtonian theories work the way we think they do. The right-hand column has a lot of restrictions on it. There's quite a few things we can rule out. So teleparallel gravity fails as a way to enact a principal gravitational split because its connection just isn't the right kind of thing to represent inertial structure. That turns out to be a general feature of non-symmetric connections. So it turns out that we can rule out a class of theories that way. And then interestingly, if we look at the Weatherall and Manchak paper that was shown on Monday, you can show that there are some problems for certain kinds of unprincipled splits of the conventionalist kind in the GR context. So we can rule out a lot in the right-hand column. All right, so that's the preamble. I have a fairly sort of straightforward structure. I'm just going to talk very briefly about the gravity-inertia split in the Newtonian context, just to set it up as a foil for when we're thinking about the GR context. Then I'll talk about the gravity-inertia split in the context of general relativity, namely teleparallel gravity, and then briefly talk about the possibility of arbitrary gravitational splits. Right, so I'm going to assume quite a lot of familiarity with things like Newton-Cartan theory, geometrized Newtonian gravitation, but very briefly, this theory has a structure something like this, right? We have a metric, we have a couple of metrics, a time metric and a spatial metric. We have a connection, and we have a mass density. And there's no gravitational field in this formulation of the theory, right? We just have a derivative operator that's compatible with both metrics, and that derivative operator has curvature in response to the mass density. In particular, it's governed by the geometrized Poisson equation. And if you impose some other constraints, you get out a unique derivative operator. And that theory has a good claim to be one that reduces gravity to inertia. As I said, this is riding somewhat roughshod over these subtle points that were being made in the first talk. This is taking the conventional viewpoint. Perhaps you might think that my defense of the conventional viewpoint in GR, I'll sort of come full circle, because by pointing out how difficult it is to make a gravity-inertia split in GR, you might think that that tells you something about how deep the unification goes. But for the moment, I'm going to just take these theories to be, well, reductions, really, rather than unifications. So according to this theory, so-called gravitational effects are really inertial effects. They're just a consequence of the curvature of the connection. So freely falling particles follow geodesics. So here's our geodesic equation. And I want you to put yourself in a mindset where perhaps that's the way Newtonian gravity had been taught to you, and you had this lovely, elegant, unified theory, and that you knew that gravitational effects were really just inertial effects. And then, someone came along and said, there's this chap Newton, and he wants to tear these things apart, and maybe we should have a go at that. So how might you reintroduce something like a gravitational field, a gravity-inertia split? Well, one way to do it would be to introduce a flat derivative operator that's compatible with both the spatial and temporal metrics, and introduce some gravitational field that looks like this thing, satisfying Poisson's equation. And you might be a little unhappy with this. So if anyone's listened to other talks by me, you might be surprised at the angle I'm going to take here, and so I should at least say, I would be unhappy with this, right? This prescription's inelegant. For one thing, both our gravitational field and our derivative operator are subject to a kind of joint gauge freedom, and they're highly underdetermined. So really, if you'd started from the geometrized perspective, this would seem like an unnatural move to make. But, we can at least get out something that makes this look very much like a gravity-inertia split. So the connection and gravitational field of our new theory are related in this systematic way to our old curved connection. We can just carve up the geometrized Newtonian gravitation connection into a standard Newtonian gravitation part and a part that's a function of the gravitational field. And our geodesic equation turns into what looks like a force equation. It describes acceleration under a force relative to a flat connection. So there's a good sense in which we really have enacted a gravity-inertia split in this context. Now, as I said, I think that, in fact, the case for getting rid of this gauge freedom and moving back to geometrized Newtonian gravitation is very compelling. But what I want to highlight here is a contrast with the GR case, because I'm going to argue that in the GR case, or in the attempt to do this, the move back to the geometrized formulation is sort of compulsory, not just compelling. So you might note in this context, there's nothing formally wrong or conceptually incoherent about imposing this gravity-inertia split. As long as you can tolerate the underdetermination that accompanies taking seriously gauge quantities, and generally we don't want to tolerate that, and we want to get rid of gauge quantities, but it's something like a kind of heuristic drive to avoid under determination that's motivating us here. And if we try and split gravity and inertia and GR in this teleparallel way, I'm going to argue the case is actually completely different. You don't just have a gauge freedom, you will. But apparently attractive options just turn out to be completely untenable for kind of conceptual reasons. You just can't. These things that look like they might be candidates for representing inertia turn out not to be. Okay, so that's the Newtonian prelude. Let's move on to the general relativity context now. I'm sure you're all very familiar with GR. We have a metric field that I'm really not going to talk about a great deal because I'm going to be interested in inertial structure, and the most natural representative of inertial structure is the connection. So although we have a metric field that, of course, responds to the stress-energy tensor via Einstein's field equations, what's important is that given a solution to Einstein's field equations, given a metric, we have a unique Levi-Civita covariant derivative. And we get it uniquely because we impose the following two conditions. We demand metric compatibility on the one hand. That's this equation 9. So we demand that the metric be covariantly constant with respect to the connection. And we also demand symmetry. We demand that the connection be symmetric in its lower indices. This criterion 10, I'll say why we demand that one in a second. And that's what we need in order to get out a unique Levi-Civita covariant derivative. And then, of course, much like we did in geometrized Newtonian gravitation, we have our geodesic equation. And significantly, those geodesics, and as defined by that geodesic equation, right, they're defined as the paths that parallel transport their own tangent vectors. They coincide with the geodesics of the metric, defined as paths of extremal length. We impose the symmetry condition, so we impose this condition 10 precisely in order to ensure that that happens. If you don't impose it, you don't end up with a coinciding class of geodesics. So it's kind of an elegant bit of GR that you happen to have a single set of geodesics. You have these two conceptually distinct notions of geodesic that coincide in this particular case. And I think it's important to bear that in mind. And of course, interpreting geodesic motion as inertial motion and helping ourselves to the kind of subtleties about the strong equivalence principle that Harvey was just talking about. In fact, the story as to why we think these things are inertial frames is a subtle one, and it involves how things behave and what the other laws do, etc. You can see that general relativity reduces gravitational effects to inertial effects. All right. So what if we want to do to general relativity what we did to geometrized Newtonian gravitation? Could we find this alternative connection, a bit like the one of standard Newtonian gravitation, relative to which you can assert the existence of a gravitational force on freely falling bodies? And it's absolutely obvious to anyone who's done a kind of primer course in GR that it's not going to be straightforward, right? Because the Levi-Civita connection really notably is unique. There is only one Levi-Civita connection for a given metric. That wasn't the case in Newtonian gravitation. There's a huge class of metric-compatible connections, and we could play around with them in all kinds of ways. But here we have a unique connection. So we're going to have to give up one of the conditions we imposed on the Levi-Civita connection if we want to find another connection. So we have to drop metric compatibility or symmetry. There are lots of interesting options if you drop metric compatibility, and I'll say brief things about them. But what I want to look at is the fact that it turns out that if we relax the symmetry condition, you can create a theory that has a really remarkable formal appearance of recreating a gravity-inertia split. And this is this theory called teleparallel gravity. So maybe I should put a proviso in here that I'm sure there are people who work on teleparallel gravity who don't think that it has to be interpreted as enacting a gravity-inertia split. But there's certainly a very big group of people working in South America who think that what they've stumbled on is an empirically equivalent competitor to GR that returns gravity to its status as a force. And they're very explicit about this. They discuss the inertial structure of the theory. They're convinced that it enacts the gravity-inertia split. And the next few slides are going to explain why. I mean, if you look at the surface structure of the theory, this is very compelling. So this is a kind of Poincaré gauge theory, but I'm going to kind of suppress its Poincaré gauge theory features for the purpose of ease of exposition here. What's important for our purposes is that it involves the Weizenbach connection, which is a metric-compatible connection which has torsion but no curvature. So you pick a flat metric-compatible connection for this theory. And if you don't know what torsion is, torsion, for our purposes here, let's keep things simple, it's just a measure of the non-symmetry of the connection given by this equation here. So demanding symmetry is equivalent to demanding zero torsion, and we've relaxed that constraint, but imposed a zero curvature constraint. And it turns out that if you crank the handle and you play around with the formal structure of this theory, the thing that looks a lot like the gravitational field strength in this theory is given by the torsion tensor. And one way of seeing that, there's several, they come up with sort of analogues of the Lorentz force law, etc., and Lagrangian and all kinds of other things. But one thing you might notice that our equation of motion, our previous geodesic equation, now looks very much like an equation that's saying that we deviate away from the teleparallel connection, the geodesics is defined by the teleparallel connection under the action of the gravitational field torsion. And at this stage, things are looking very like the Newtonian case. So I can make the parallel go further. I can point out that, look, our curved connection has been split into a flat inertial and a gravitational part. So the Levi-Civita connection gets split into, I've missed the TPG off the top of that connection, but I mean that to be the Weizenbock, the teleparallel connection. And the difference is something called the contortion tensor. And the contortion tensor turns out just to be a simple function of torsion. So what we've really done here is we've split our curved connection into a flat connection and something very related to the gravitational field. So that looks really analogous to the relationship between geometrized Newtonian gravitation and standard Newtonian gravity. And there's various ways you can get to the equation of motion on the previous page, but one way would just be to substitute this thing into our geodesic equation. In fact, although this isn't what they explicitly do in the papers, because this would make the theory look a little too close to comfort to general relativity, but in fact you can generate all of the equations of teleparallel gravity just by, wherever you see a Levi-Civita connection, subbing in this term and cranking a handle, and you'll get out the entire theory. That's a proof of empirical equivalence.
Subbing in which term?
The 14. So sub in the...
Curly bracket term.
So subbing in for the Levi-Civita connection, where it appears in GR.
You put in the curly bracket guy.
No, put in the gamma minus k term wherever you see curly brackets in GR. And then they do a lot of things to make it look pretty and look further away from general relativity, but secretly. And they do derive things from the action, and they do some fancy mathematics. But in fact, the relationship's a little closer than they tend to admit. And one thing I'm suppressing here is I don't think this is a distinct theory. I mean, I just think this is a trivial reformulation of general relativity, in fact. But that's not the thing I'm sort of worried about here. You could take this analogy with the Newtonian case even further. You could say, look, the Weizenbock connection is actually subject to a gauge freedom in much the same way that the connection in standard Newtonian gravitation is. So you might think we're in a position very like the Newtonian case. We can force this split if we want to. It's a kind of conceptually coherent split, but it's sort of untenable in that we would want to move back to the formulation with no gauge freedom if we could. But I actually think that the situation is much less analogous than all of that appears. So that's the kind of line that somebody who wants to push this split is going to give you, although perhaps without the gauge, eliminating gauge freedom considerations. So once you start digging around in this theory, you start to suspect that this thing that they're calling the inertial connection, the Weizenbock connection, doesn't do any of the jobs it's meant to. It just doesn't do what it says on the tin. So there's a metric hanging around in this theory. Another aspect of this theory I've been not mentioning is that generally it's all written in the tetrad formalism, which makes the metric not look very explicit. But whenever you have a tetrad, you secretly have a metric because you have an orthonormal frame, right? An orthonormality is defined with respect to a metric. So the general relativistic metric is still hanging around in the background in this theory. And so there are actually two classes of geodesic in this theory. One class of geodesic belonging to the Weizenbock connection, and another class of geodesic belonging to the geometric. And it's empirically equivalent. So freely falling bodies are still trotting along geodesics of the metric. And then you start to look more closely and you realize they actually do something, introduce something called the teleparallel covariant derivative, which turns out just to be the Levi-Civita covariant derivative. So the non-gravitational interactions, in fact, still couple to the Levi-Civita connection. So minimal coupling holds with respect to the Levi-Civita connection. Unsurprisingly, because this is exactly equivalent to general relativity. And even conservation laws, of course, are defined with respect to the Levi-Civita connection, not the Weizenbock connection. So this turns out all to be a bit tricksy. So you really end up thinking, hang on, I haven't managed to split anything off, have I? And the Weizenbach connection doesn't seem to represent inertial structure at all. It's not playing the same role that the Levi-Civita connection did, and my Levi-Civita connection is still hanging in there, playing the same role, just written down in a gerrymandered form. That would be pretty compelling, but I think the problem is actually, in fact, even deeper than that. And what's interesting is it's a general problem about trying to introduce a non-symmetric connection and insisting that it represents inertial structure. So there's a good case that non-symmetric connections just aren't candidates to represent inertial structure in the kind of way that Levi-Civita connection does. You might introduce a non-symmetric connection for all kinds of other reasons. They might be useful for other things, but they don't represent inertia. And one way to see this, I haven't gone into kind of all the formal details here, is to point out that, look, let's call a frame normal if the connection coefficients vanish in that frame. And we'll call it holonomic as long as we can define coordinates associated with the frame. So here a frame is just a tetrad of basis vectors. And we either can or cannot, one, make the connection disappear in that frame, and two, associate coordinates with that frame. And in general relativity, we can't define these kinds of frames globally. We don't have global inertial frames. We do have local inertial frames. We can define them along a curve. And the coordinates associated with those kinds of frames are Fermi normal coordinates. And Fermi normal coordinates are defined along a geodesic are exactly what we think of inertial coordinates in GR. So we have this special class of coordinate in GR that have a special relationship to our connection. And in the presence of torsion, there just are no holonomic normal frames along a curve. We cannot do this trick along a geodesic in the presence of torsion. I mean, the quick and dirty way to see that is that when you write things in a coordinate basis, and this is a little bit tricksy because sometimes they write everything in a frame basis and they can kind of get around this, but the important thing is that there aren't coordinates that correspond to this. When you write torsion, when you write a connection in a coordinate basis, that's the situation where that equation I gave you for torsion applies, and torsion just is the antisymmetric part of the connection, and that's a tensor. So you can't transform coordinates and make that tensor disappear. That's what a tensor is, right? So we can't define Fermi normal coordinates in the presence of torsion. And that means there's no natural analog here of the structures that represent inertial frames in general relativity. And so the claim here is that non-symmetric connections just aren't candidates for representing inertial structure. So whatever you're doing when you introduce a non-symmetric connection, you might be doing lots of useful things, but you're not introducing a new set of inertial frames. Okay, so let's have a look at how our table's doing. This side is entirely intact, sitting there perfectly happy, but this side has quite a lot ruled out. We've decided we've ruled out teleparallel gravity as a GR context principled split. We've ruled out any other theory with a non-symmetric connection. I've split up our conventionalism category into a little more here. I've said, look, you could have conventionalism using non-symmetric connections, or you could have conventionalism using symmetric connections, and we've ruled out that class of conventionalist theories too. So we've ruled out quite a lot of possibilities for splitting up gravity inertia and GR. And just in the last couple of minutes, I just want to point out that one result we've seen at this conference, which I think can rule out quite a lot more. So I imagine lots of you were at the talk on Monday, so I'm only going to do one brief slide on it. But look, this paper by Jim and John shows that looks at what kinds of conventionalism are possible in Newtonian and relativistic contexts, right? And points out that although Reichenbach's own prescription doesn't work in the Newtonian context, there is a perfectly reasonable way to split the geometrized Newtonian gravitation connection into an arbitrary connection and some function of a rank 2 tensor. And that rank 2 tensor is going to have the right kinds of properties to represent a force field. So in Newtonian gravitation, this kind of arbitrary conventionalist gravity inertia split is possible. But they also show that something similar is not the case in GR. So there's a no-go result that shows that you can't find a suitable rank 2 tensor, and the suitable rank 2 does a lot of the work there, relating the Levi-Civita connection of two conformally equivalent metrics. So they're working with symmetric connections only, but you can rule out a whole class of possible split options here. You can relate any two connections via rank 3 tensor, and it's not quite clear whether that kind of tensor can represent a force field. And maybe one thing to say about the teleparallel case is that torsion is a rank 3 tensor, and perhaps if I dug more deeply into thinking about torsion as a field strength rather than dug deeply into thinking about the connection as an inertial field, you would have found an analogous argument that torsion just wasn't the right kind of thing to represent a force at all, despite the superficial appearance in the equation of motion. So there's thought to be done here about whether we can enact a gravity-inertia split using rank 3 tensors. So where do we end up? I'm not suggesting it's impossible to enact a gravity-inertia split in general relativity, but it's remarkable that we've crossed out a lot of things on this side and nothing on this side. So some of our instincts about this idea that we can reintroduce gravitational fields are very Newtonian. It's really easy to do because of the kind of looseness of Newtonian geometry. But it's really remarkably difficult to do in GR. We're left with possibly introducing new metrics or non-metric compatible connections, rank 3 tensor conventionalism, but not much else. So in conclusion, I think it's not a no-go result. But it's I think interesting and tells you a bit about how intimate the connection between gravity inertia is and GR. There are possibilities for imposing a split, but they're getting pretty far-fetched. We can rule out a great many candidates that possess prima facie plausibility. And we have a great deal more freedom in Newtonian theories. So what GR has joined is not that easy to tear asunder. And that's it. Thank you very much.